Yeah, perfect. But yes, it'll all be up on YouTube afterwards, either tonight or tomorrow. So, and for the people on Zoom, if you have a question, just turn on your microphone. I'm not going to see any of the cameras. So, okay. Hopefully everyone's familiar with getting to this step. So usually the way I work is having the Grasshopper canvas on the right side and the Rhino window on the left. You can do anything you want. I do like to work in just the perspective view though, so we can see the biggest screen in Rhino. If you have any problem getting to that, you can always double click on the name of the window and that'll transition between the four, or just perspective, or just top. It really doesn't matter, whatever you're comfortable with. We won't actually be modeling anything in Rhino today. It'll all be in Grasshopper, but in future workflows, we might use curves or sub-Ds in Rhino and design stuff in there that can be used in Grasshopper. So just know we will do some hand modeling, but a lot of it will be in Grasshopper. So in terms of Voronoi, there are a lot of different options for that, and we can find most of them that come with Grasshopper under the Mesh and then Triangulation tab. And today we'll just be using the most basic one, which is just this one called Voronoi that can do a 2D pattern based on some points. And a thing about Grasshopper too is every single thing you can hover over will also give you a description. So if you're unsure of what something does, the description really helps out a lot, which you might have known from the videos. And then also with the components, and we'll get into this as we build, but if you hover over any of the inputs or outputs, they'll give you some more description as well as to what they need. So just going to show these different things. So the Voronoi we'll be starting with is just from a collection of points. If we have time, we can go on to 3D. So this will be a 3D collection of points. And there's a lot of other options as well for different niche things. But the main ones are just this 2D and 3D option. So we'll grab that Voronoi component and just pull it onto the canvas. And we'll be working around this mostly. If you don't want to grab a component from the menus, you can also, as you probably know, double click anywhere on the canvas and we can just type in Voronoi and it'll pull up a list of what it thinks we want and we can select that from there too. So two different ways to get a component. Also to note, you don't have to type the entire word to get a component. You could just type the first 3 letters, or if it's a component that has multiple words like construct point or something, you don't have to type all of every word. You can just do the first couple letters of each word, and so it'll lead you to the component that you're looking for. So just some things to note. So with this Voronoi, we can see that it's asking for a couple things in order to work. We can also see that it has this error bubble that's saying it really needs this to work. For most components, you don't have to ever fulfill every input. Some of them you might, but a lot of components, you can just fulfill a few of them and it'll work. In this case, what it's asking us for is a list of points to start. And the simplest way to do that is to use, there's a couple different populate components. So if you start typing in populate, we can see we have populate geometry, populate 2D, and then also 3D. In our case, we'll be using geometry, but if you ever wanted to do the most basic Voronoi build that you could do, you could just really easily start with a 2D. And by default, this will give us, I think it's a 20 or 40 by 20 rectangle filled with points. So that's super simple. You could put some information into any of these inputs to change the size or the number of points, but by default, this is what it'll give us. And this is a quick way, if you drag the points into the point input for Voronoi, the quickest way to see a Voronoi diagram. So there's only 2 components, and we get a pretty fun pattern there. We'll be building up a lot more around this, though, so we can bring in sliders and the MD slider and a lot of other control into this. But just to show you could do that, it's pretty simple. But for today's tutorial, we'll be building a rectangle and then building 2 circles within that rectangle so we can control the size and the density of those circles, so we can get closer to what I was showing here with two different areas of density. So we'll build that up. We can keep. You could be. Interesting. Yeah. What else is it asking for in the error bubble? Oh, you're doing populate geometry. Okay. So we will be using populate geometry. That's the one with the little white cloud. The only thing this needs is a piece of geometry to put points on. So yeah, no worries. Everything should be working fine for you in Rhino 6. It will be interesting though. We probably have between 6 and 8 in this class, which the only thing 6 lacks is the ability to do sub-D modeling, but it's not a big deal. Everything else it should have. Yeah, so we'll get to that. So to start off building this rectangle that we can put these circles in, the easiest thing to do is we can start with a plane surface. And this will just give us a rectangular surface oriented about the X, Y axis. So it'll just put it flat down on the grid. So as I mentioned, it is on the XY plane, which by default, it'll just do that, which is fine for our uses today. We don't need the plane to be anywhere else. But the other two options, X and Y, we can use to control the size of the rectangle itself. The size can be whatever you want, and you can add a value to it any way you want, but the easiest way that I think to do it would be to use a slider. And in the video, you learned how to use sliders. There's a lot of different ways to type it in. The way I enjoy doing it is by putting the lower bound of the slider that you want. And this could be any number, any positive number that you want. And then doing 2 full stops, 2 periods, and then the upper bound. So that can be, again, whatever number. I'm just doing 1 to 50 to give us some range. You'll see it'll populate with number slider right above it. And then if you hit enter, it'll give you a slider between those 2 numbers. So in my case, between 1 and 50. So that works pretty well. You can do that again to grab a slider for Y, or you could just copy and paste this component with Command CV, and that'll give you another number slider. Or you could write it again and maybe do 1 to 100. Really doesn't matter though what the scale is. So with these 2 sliders, we can fulfill the X and Y values. And now we can get a rectangle that changes scale based on these sliders, which is pretty nice. Is that working for everyone, just to get a simple setup? Yeah, cool. Okay, so now that we have this surface, and it's important that it is a surface for the next step. In the tutorials, I believe they went over some of the different geometry that are in Grasshopper and Rhino. You've got surfaces, B-reps, curves, meshes, sub-Ds, and each one has its own properties. In this case, what we're going to want to do in order to get those circles is we have a rectangle, but we can put some points on that rectangle inside of it, and we can use that to control the density around them. So what's the easiest way to put points on the surface, and more importantly, bound them within the surface? We don't want them to leave the constraints of the rectangle, because then we might get some weird issues. So how do we do that? There's a lot of ways to evaluate surfaces and find points on them. And all of that is going to be in the Surface tab and then in Analysis. So that's where we have a lot of different components that can do a lot of different things. Today, though, all we have to worry about is this Evaluate Surface component. So you can grab it from here, or you can type in Evaluate Surface. What this one is going to do is it's going to take our surface, and it's going to take some input numbers and then find a point that's within that surface. The surface does not have to be rectangular. It could be curvy, say if you were lofting some curves together. It doesn't have to be flat. And the points will always stay bounded within that surface. So on top of the Voronoi question from earlier, does anyone know what UV values are in terms of 3D? A little bit? Care to explain? Mm-hmm. Yeah. Very simply, it is just coordinates. Since we don't have to work in a flat surface, the surface could be curvy, it could be like hilly and mountainous. The UV would just define a point kind of based on the XY of wherever it is on that curvy surface. So hopefully that'll make sense in a second. What we can use to define the UV value is we could type in numbers. So if we had a rectangle like we do there, and say this is 0, 0, we've got the U and the V axis. So we can call this 0, 0, we can call this 1, 1. If we wrote a number like 0.5, 0.5, that's going to be right in the center of everything. And then if we did any smaller values, any bigger, it would get closer to one of the sides or the other. So we can do that with a multi-dimensional slider. So if you type in MD, we'll grab that. This will output those two numbers. So it'll output anything between 0 and 1 for both U and V. So we can grab one of those. And if you pull this point around, we can see those numbers visually on the screen as well, going from 0, 0 up to 1, 1. So if we plug this all together in the evaluate surface, we have the surface and we have the UVs. And we can look at Rhino and see what's happening as we move this point around. So we can see we have a point in the bottom left there with an XY plane around it, moving away from the origin point, but not moving too far. Right now, it's moving from 0, 0 on the grid up to, let's go to the point, up to 1, 1 on the grid, which isn't too much travel in the scope of the entire rectangle. So how do we solve that? There's not much we can do with the MD slider to change where the endpoint is. And it wouldn't be smart anyway to do that because we could change the size of the surface. And now, if we were to put this at 50, like it was a second ago, that would not matter anymore because now the rectangle is smaller. So how do we have those things kind of talk to each other and know that 1, 1 is just the max and 0 is the minimum? Really easy thing we can do to fix that, if you're familiar with right-clicking on any of the inputs or the outputs, you'll know we get this list of options that we can apply to any of the inputs. And we can do that to S, we can do that to UV, but you will see there's a different option here on a surface or a curve, but right now we're just doing surface, called reparameterize. So basically what this is doing is it's taking the rectangle and the bounds of the rectangle, the domains. Right now 0 to 50 is the length of that rectangle. It's going to take that 0 to 50 and remap it to be within the domain of 0 to 1. So 50 now becomes 1 and 0 will stay at 0. So we can just click that in and we'll see this little graph pop up saying that we're reparameterizing the surface. So at this point, when we put the MD slider to 1, 1, we're getting max travel on that rectangle, and 0, 0 will go back to the bottom. So now it's mapped correctly to the entire bounds of that rectangle. Hopefully that makes sense. Hopefully you know how to use it. It's pretty easy. If you see it not working correctly, you can always just try to reparameterize and see if that fixes things. In our case, it'll be more interesting to have 2 points on this rectangle so we can control density in 2 different areas. There'll also be some more thinking that comes with having 2 points existing on one surface at the same time. But to start, it's really easy to put 2 points. We can just duplicate this MD slider, Control C, Control V again. And we can plug both of these MD sliders into that UV input at the same time, and we'll get 2 points on the surface. There's a couple different ways to put 2 different data types into a single input. If we try to drag from the second one into the UV, we'll see that it kicks out the first one. So again, we only have one MD slider going in. If we do the first one again, it's going to kick out that second one. So there's 2 different ways to put these both into the same input. The first one, we could use a merge component. And what this will do is it'll take multiple different outputs, inputs, and assemble them together into one data stream. So now we just have one wire coming out. That's one way to do it. And if we plug these both in, now we have both points existing on the surface at the same time. So you could do it that way. Another way that we can do it if you want to have less components on the canvas is we could put the first MD slider in, and then we can take the second one, and before we let go of the mouse to put it in, if you look closely on the mouse, it's probably better if you look closely at your computer, but if you hold down Shift as you drag, that little arrow on the mouse will turn green. That's just showing us that we can add another wire into the same input. So as we're holding Shift, if you let go on the mouse, it'll put both wires into the same input. So they do the same thing, having the merge or doing it this way. This is just a little bit cleaner. Okay, so at this point, now that we have these 2 points on the surface, the evaluate has a lot of different outputs. We don't have to worry about many of them except for the point at UV. This is the only one that we need right now in a 2D space. With that point, what we can do is we'll think about how we're going to populate 2 different circles around these points. But the first thing we'll do is actually define the circle and define the radius of that circle so we can control the density of the points. The easiest way to do that is to use a primitive circle. And this will just give us a curve in the shape of a circle around points. So if we take the points and plug it into the point input here, you can see we have 2 circles on the rectangle now. As I'm working in Grasshopper, I also like to preview off any older components just so they don't clutter up the scene. The evaluate had these big rectangles around it. It's hard to see the circles with them there. So if you right-click on the icon of any component, you can just hit the preview button. It'll preview it off. I'm also realizing I'm not sure if it was in a tutorial or not, but you might have words on the components that say evaluate surface, not the whole thing, but an abbreviation of that. You might have images. Right now I have both just so you can see the words and the pictures at the same time. But that's a plugin. So if you wanted to see maybe the images instead of the writing, you can just go to display and draw icons and toggle that back and forth. I seem to prefer the images just because it's easy at a glance to see what's happening rather than trying to read the words, but up to you which one works best for your workflows. But just know that that is available. Okay, so with the circles, we'll want them to be different radii. The easiest way to do that is going to be to use sliders this time. We don't need multi-dimensional sliders, we just need one number. And again, we can make these sliders as big or small as you want. I'm doing 1 to 20, but I don't think it really matters. Yeah, it's going to be easily big enough. Because we have 2 circles, we'll also want to have 2 sliders. So we can duplicate the slider to have 2. And then same process as adding 2 things into an input again. We can click and drag and then click and hold Shift to add the second one in. Doing it this way, though, you will have to remember the order that you're doing it. If we did this first MD slider and then the second one, for visual clarity, we'll also want to do the first number slider and then the second number slider. If we did it out of order, we would also see that it would be out of order on the canvas. So if you're not using a merge component, just make sure you're doing, the top one first and then the bottom one, or however you like. So at this point, we can see the first slider will control one circle and the second one will control the second circle. Okay, so we'll populate these 2 circles with points so we can add them to the Voronoi. But in order to do that, we'll have to convert it to a surface so we can actually put points on a physical piece of geometry. The curve itself wouldn't do much. We want points on the inside. So we can do that by grabbing this surface component. So you can type in surface, you can type in SRF as an abbreviation, but we just want this black hexagonal icon. That'll give us surface. If we plug the curves of the circle into that, it should light up green, and then we'll see we have a filled in circle. Hopefully that's working for everyone. Okay, so at this point now we can start adding points and moving towards fulfilling some of the inputs for Voronoi. So we can use the populate geometry this time, the little white cloud icon. And this one by default comes with 100 points in the N input, but we'll be adding something to change that in a second. But the important input right now is the G for geometry, and we can add both of the surfaces into that. And you should be seeing points populating within the two circles. If they're just on the perimeter of the circle, or if they're not even in the circle at all, you might have a different issue, but hopefully they should be just inside both circles. You might wonder why we can't use the populate 2D in this sense with the circles. I'll just demonstrate real quick. The populate 2D also needs a region, and we could use the circles as regions as they are curves. But we'll see that it needs an actual rectangle to populate within, which isn't going to be too nice for us because it'll just look better within a circle. So we can get around that by using populate geometry, which is nice. You'll notice now, though, that the small circle is more dense than the larger one. If you want to control that, you can. And again, we can do that with some sliders. In this case, it's starting out at 100. So we might want to make the sliders a little bit bigger this time. I'm just going to go from 10 to 200. But you can do however much you want. If your computer can't handle too much computation, you might want to keep the numbers low. But if you have a computer from the last couple of years, you should be fine doing bigger numbers. Just some problems we've had in the past. But again, just like the previous two times, we'll have two sliders for both circles. And we can plug these both into N. And now we can control the density separately. Also, an optional thing you can do here is the populate geometry does have a random number generator within it to populate these points in a random orientation. But right now we have one of those random outputs. We could do different random outputs though. And in any of the components that deal with randomness, they always have a seed input. So right now this seed is telling us we have number 1 of randomness, but we could do any number of randomness to change it. And this is optional, but all it would take is a different number. So right now it's at 1. But if we were to change that, we can see we get different randomness in those two circles. So again, this is optional. It's not going to make a big difference today with the final visual of it. But just know you do have this option. If you don't like the first randomness, you can take a chance on the second randomness, and so on up to infinity. So. Okay, at this point we have points, and we can plug these into the P input for the Voronoi. As we do this, though, you'll see the cells only really exist around the circles, and they don't exist in the rectangle itself more generally. So the pattern isn't complete yet. You might also notice that we have two different kind of rectangles, one around each circle. And that's just because we have this dotted line now going out of geometry and into Voronoi. And this dotted line is telling us that we have a list of data on two separate tree branches. And we can kind of see what that looks like. You don't have to do this step, but just to show. we can see that we have data with two branches. The first branch has 28 items, the second one has 149 items. And we can see that lines up with the amount of points that we set, and that'll change if we move these numbers. So all it's telling us is that the Voronoi operation is now working twice, once for the smaller circle and another time for the bigger circle. It's not working together with both at the same time. I believe the video tutorial recordings went over data structures a little bit. It is a topic that is more high level within Grasshopper, but it's not something you need to worry about too much unless you're doing very custom things. In our case, though, it's really easy to fix this to have them work together, to put them within one rectangle. And that can be done, let's see, by just flattening the input. So again, we right-clicked and reparameterized the last one. In this case, we can hit flatten, and that'll take both of those branches and just put all the points onto a single branch. So it'll do the operation once for both lists. And now we can see that the cells are now interacting on this line between them, and they exist now within one overall rectangle. So is that working for everyone? Does that kind of make sense? Yeah. It doesn't. You can think of it now as it gets to Voronoi, it's dotted, but as it enters, it'll be a single line. And we can visualize that too. I'm just going to unflatten this for a second. There are components for these things, so we could use a flattened tree, and we can plug the dotted into there, and it'll come out as a single line showing that it is now flat. But yeah, it's also, if it has the icon, then it will be flat going in. Another thing too, if we had it like before, we can hover over the output of P, and we can see that we have those two branches with the number of points. But if we hover over the input, we can see that we just have one whole list of the total number of both sets. So it now has everything in here, so you can see that visually if you like. So one other thing, since we just have the points within the circles, we also want the points within the rectangle, so we get a really nice pattern overall. And we can just use another populate geometry for this and use the original rectangle itself as the one that will define this population set. So we can take that original plane surface. You might have to zoom out a little bit. But if you run the wire from the plane surface to populate geometry, we'll get points within the rectangle itself. So now we have a set of points from the rectangle and another set of points from the two different circles. We can combine all these point sets together into one set of points and use that for the Voronoi. But before we do that, we might have some instances of points that get really close to each other, like in this instance. And that might lead to really, really small cells. That might throw the look of the pattern off. And it just gives me an excuse to introduce another component. But if you have this option of maybe some of your data, maybe some of your points are too close together to be nice for the overall pattern, something we can do to kind of clean up the set of data is there's a component called col duplicates, col meaning delete. So what this will do is it'll find duplicate data that is within a tolerance, so that will be the T input, and the tolerance is the distance between two pieces of data, and if it's within that tolerance, so it's too small, it'll just delete the points and kind of clean up the list a little bit. So we can run all of the points into P, so we'll run one and then holding shift, we can run the second one in. Important thing to do here is we want it to check all of the points together. So we'll want to make sure we only have one branch. So we don't want it like it is right now where there's two separate branches. So again, we can flatten that, and we want to see all the points in a single list. So now it can check all the points against all the other points. And if it finds anything too close, it'll get rid of it. But we can define what it means by too close. Right now, the tolerance is 0.1. which might be really small, and I don't think it's finding any close relationships at the moment. But we can change that with a slider. So I'm just going to start at 0.1 and go up to something large, I don't know, like 10 or something. So now with this slider, we can control what is too far away. We can plug that slider into T, so the tolerance value. Right now, nothing should change because it was 0.1 to begin with. But as we bring the slider up, we can see that our green dots are getting less and less as that tolerance gets bigger. So let me turn off some old things that might be in our way. And now we can just see the points. So we can visualize this real quick. Let's see. And you don't have to do this step, but just to show what it's kind of doing here is, say we had circles around every single point using the tolerance as the radius. As we make the radius bigger, we can see the circles get bigger, and as they start touching each other, let's actually use this list. It'll start deleting the ones that get too close and trying to kind of organize them all within that radius value. So just visually what's happening is we can see kind of in this set where they start to touch. This one right here, if they get too close, it'll delete that one, and we'll be left with a cleaner set of data. This tolerance is quite large. We don't need this much because we still want to see some detail. We don't need this circle, so we can make it a little bit lower. So whatever looks clean to you will work nicely. So at this point, now that we have all the data together and it's been cleaned, we can replace the wire that we had before in the Voronoi with a new set of points. So this is everything. So now we can see a Voronoi diagram that includes all the points, the densities of the two circles, and the points in the rectangles themselves. So that's pretty nice. But we might notice that the cells extend over the rectangle pretty far, which isn't ideal. So we can explore some of the other inputs for the Voronoi. Second one, optional cell radius. It's not going to matter too much for us. The third one down there, the boundary. This will actually constrain the diagram within any boundary we set. It'll have to be a rectangular boundary, which is fine because we have a rectangle to start with. And we can actually use that rectangle for the boundary itself. So we can zoom back out to the plane surface again, and we can use this surface as the input for B, for boundary. And that'll actually bound the diagram within the original rectangle. Okay, so we've done a couple things. Is that still working for everyone? Working good? Cool. Okay, let's see. At this point, we just have curves, and we have one curve for every cell. You don't have to do this part, but just to visualize, we can see that each cell has its own boundary, and we could flip through all of them. You don't have to do this part, but just to show, let's see. We can flip through them all and see that each cell, it looks pretty nice. All of them are pretty clean, which is good to see. But now, like the example from earlier, we can actually thicken all of the lines. So we can start adding another layer of detail onto this that isn't just curves. So there's a couple different ways to thicken a curve or a line. The easiest way, though, is to use a pipe component. So if you type in pipe, it'll be this little orange circle or orange tube. But I would hesitate on plugging in the diagram to the pipe component just yet. The pipe component can be kind of slow at times. So I'm just going to take down these numbers a little bit. Maybe also take down the number in the rectangle as well, just so things run a little bit quicker. Up to you, though. Okay, so if we were to take the Voronoi curves and plug them into the curve input for the pipes, We'll give it a few seconds, and then we should start seeing some thickened curves showing up. It's a little bit messy at the moment, but we'll do some things to clean this up in a second here. But hopefully that is working, and it's interesting.
I don't know if I just missed the step in connecting the service to the Voronoi, but when I tried to work that.
Okay. I mean, you see this diagram, yes? Yeah. Okay, and you're plugging just that output into the input for pipes? Interesting. There's another thing we could try. What Rhino version do you have? Okay. Do you have a component called multi-pipe? I believe you should with Rhino 7. Rhino 6 might be a question, but yeah? Okay, let's try that one. Try multi-pipe. And if we plug the curves into curves, let me know if you see anything.
No, it's still just basic.
Still the rectangle. Interesting.
Did you connect the surface to the original Voronoi?
Yeah, there's the diagram. Let me come take a look at it. My microphone. It might just be that something wasn't done. Yeah. Yeah, I'm using multi-pipe, which I believe is reference 7. I pointed it and I was like, they're yeah. Yeah, so if you zoom out to see everything, we can drag over all of the old components, so everything except for the pipe. And if you right-click just off the canvas somewhere, you can preview everything off. And that should get rid of the old set of pipe or points that are kind of clogging up the visual space. Oh, okay, okay. Take a second. Wait, what do you mean? Oh, yeah. Yeah. Mm. Okay. I still sound good on Zoom? Yeah. Cool. Okay, if you're using multi-pipe or you're just using pipe, both should do the same thing. The pipe might be a little bit messier just because it's an older kind of component. The multi-pipe looks pretty good. One other thing we can do to this is actually control the radius of the pipe based on how dense it is. If we have the dense section be the same thickness as the not dense section, it's kind of, there's a lot of mass in that area, and we could lessen that a little bit with some math. So we'll do that next. We can just leave this up. We're not gonna change anything just yet. Okay, so we can control the radius of the pipes in the more dense sections based on their distance away from either of these original 2 points. So we have those original 2. What we can do to start is just grab both of these points separately, and then we can start measuring distances. So in order to do that, there's a component called list item. What this will do is it'll take any list and it'll output any item based on the index that we set. So I'll explain what that means. But to start, we can take the points from P and wire those into L for the list. So any set of data is just a list. So the input and the output letters don't have to match. So yeah, we'll take the points, put them into L. So right now, if you zoom in, we can see that we're getting this first point. It's a little bit messy with all this turned on. But you can see as I click, we can get that point to light up. So right now, it's selecting whatever the first point is. And that's because by default, the item index is set at 0. If you know anything about computers, how they work, the first number in binary is always going to count at 0 and then go 0, 1, 2, 3, and up. So the first item is always 0. The second item would be 1. And we could put in 0 and 1 to get both items. But a nice thing about this list item component is if we zoom in really far into the component, well, not too far, but we can see we get these little plus icons that come up when you zoom in. This is nice because we can zoom in and click the plus button below I, and we'll get I plus 1. So this will be index 1, this will be index 0. So now let me zoom out a little bit. We can see we have both points showing up on this list item. So now we have an output first for the first point, so point 0, and then 1 for point number 1. And now we can use both of these points separately to do some measurements on. Okay, so we have, again, we'll need all of the points from the component just before the Voronoi, so the cold duplicates in this case, and the 2 points that we just found. So we'll need both of these. And what we'll do is we'll measure the distance between all of the points and the attractor points that we made with the multi-dimensional sliders. One thing to note, though, we have, let's just do a little drawing. So we have 2 points, and we have a whole host of other points floating around. If we found the distance between every point and every attractor point, then every point's going to have 2 different distance values, and you can't have 2 different radii values for one pipe. So we'll have to solve that. We only want 1 distance value for every curve, so we only construct 1 pipe. In order to do that, before we measure the distance, we'll want to find which attractor point is closest to every point in the cloud that we have. So I'll do that and then show what's happening. But to do this, we'll need a component called closest point, just the singular version of this, closest point, no s. So we'll grab that. All of the points that we had before from cold duplicates, we can see we have two inputs here, the points to search from, so the starting point, and then the points to search onto, so the ending points. In this case, we'll want to put the whole cloud of points into P to start. And then we want to find which attractor point is closest to any one of these cloud of points. So we'll put both of the points, holding shift again, into C. So these are the points to search onto. And now what this has done is it's found for every one of the attractor points, it's found the closest point in the cloud. And visually what this has done, you don't have to do this step, but to visually see what's happened. We can see if we make a diagram of the lines from the output of this closest point component to all the original points, we get a really nice delineated set of data. So only the points around each of the attractor points are looking towards that one. If we were to not do this step and just do a line from every point to every attractor point, we have this overlapping list of points that, as I was drawing a second ago, is going to give us 2 lines for every point because we have 2 attractor points. So we clean that up with the closest point, and now we only have 1 line from every point to every closest attractor point. So that's pretty nice. Hopefully that makes sense visually. But we don't actually need these lines at all. The closest point component gives us the distance as well. So that's nice. We don't have to do an extra step. And we can use this distance to control the radius. So we could say, actually, let's get that line back. We could say any of the super long lines, we can give a really big radius because we know the cell is probably going to be really big. And then any point that's close up that has a really short line, we can give that a small radius. Because, again, this one was just, there was 1 radius for everything. And when we get up close, the radius gets quite tight. So we can vary that with this distance value. So now we have all these distance values, and we can use these for the radii, as I explained, but we might not want, you can see this list goes anywhere between 3 to 21. That radius might not look too nice because 21 is probably going to be massive. But we can, for fun, see what that would look like. You don't have to do this portion, but let's just see if we were to use these distance values, what we would get. It's great. It's doing a thing, just not doing a good thing. We can see any of the points that are far away, like something over here has a super big radius, but visually it's not working with our set. The numbers are just not in the right domain. So we can take these numbers and we can remap that domain to be within something that looks nice. So just like with the reparameterization from earlier, we can take the domain, say 20 is the largest number, and we can constrain that down to a nice value like 1 or whatever we want for a radius. And we can use the component called remap numbers to do this. We can't just reparameterize into 0 and 1 because that 0 to 1 domain might not be exactly what we want. What remap numbers gives us is we can actually set a target domain for the radius that looks nice in our sense of things. So this might not make too much sense as we build it, but hopefully once we add the sliders in, we can start playing and seeing what's happening. So to start, we have all the distance values. So this is the list that we want to remap. So we can see V is the values to remap. So we have those. And what we don't have yet, though, is the source domain. So what is the lower and upper bound of these values? And we'll have to figure that out. By looking at it, I could say it might be between 3 and 20, maybe, but that's not a good answer. We can use a component, though, called bounds. And that'll take any list of data, any list of numbers, and it'll give us the domain that sits within. So we can run the distance values into the numbers input, and coming out we can see that the domain is between 0.3 and 21, just about. So this is the starting domain, so what the list started at. So we can use those numbers going into S. Let me just move everything real quick. So we can use that starting domain as S to give us a starting point so we know what we're remapping from. And then we'll need a target domain. So what do we want to remap to? By default, we're remapping to 0 to 1, which is smaller values, but we can't have a pipe be at radius 0 because it needs to at least exist. So we can construct a new domain that has a new set of data, or a new set of lower and upper bounds. So in order to construct a new domain, we can type that in. We'll construct a domain. And with this construct domain, we'll just have to define what the lower and upper bounds are. So again, we started at 0.3, and the larger was 21. But as we can see, that's very, very big. So we'll want to make sliders for our new domain. So we could start within that range and find something that works. So I'm just going to start with 0.01 and 20. That's kind of where we started. And we can duplicate those two sliders. So now we have a slider for A and a slider for B. Right now, if we go lower and higher, we have 0.01 and 20. That's kind of where we started. We know those numbers are wrong, but at least we have a starting point, and we can move these sliders around to find something that looks better. So we can go ahead and plug those into A and B for the construct domain. Once those are plugged in, we can put the construct domain into the target input. And now what this has done is it's remapped our original list of numbers to now fit within this new target domain. We can use these new numbers as the radius values, but I would hold off if you're using the pipe component or the multi-pipe, because it might take a couple seconds to actually do the calculation. So I'll do it up here first, and then hopefully you can redo it on yours with some good numbers. But just to show, we can plug that remap number into the radius. And right now, not much has changed. It's still the same as before. But I can start moving these sliders and finding better radius values for the different sections. So the upper one is working on the dense set. So all the points that were really close to the attractor point, this one is controlling those mainly. But we can see it's not doing much to the larger sections there. And then the lower slider is going to affect all the points that are farthest away from those attractor points. So we can see those are affecting the large ones. So the numbers are quite small here. You can probably do something between 0.1 and 1. And that should hopefully work nicely. And this will only work on the pipe component. If you're using multi-pipe, I don't think it'll work because it's going to try to put everything into one multi-pipe. But we need them all to be separate in this sense, so we can have the separate radius values for the separate curves. So the pipe component is going to work best for this. And if your computer was slow a few seconds ago, you might want to take the numbers down on things so we can play around with it and it's not going to crash.
Hey RJ.
Yeah, what's up?
What is mesh pipe under? Because I can't get it to come up.
No, it's a good question. It's a plugin. It's a really nice plugin for mesh pipes. It's on Ngon, which we'll talk about installing plugins at the end of today's class. I'm just using it now because it'll show a lot quicker on my screen what's happening. But for the actual workflow today, we'll just be using the pipe component itself that comes with Grasshopper. But any other time we do this after today's class, we'll use the plugin because it's a lot better. Okay, so hopefully with these values, 0.1 to 1, I would start there and plug these in. Just trading out mesh pipe, don't need that anymore. Trading it in for the new curve and radius values, but we'll have to give it a second because it might take a little bit. Okay, it's doing the same thing. It's just the pipe component. It's not the best, so we have some pieces overhanging. One thing we can do to kind of clean this up a little bit, make it a little bit more organic. Let me see what the component is. So if we look back at the example, we can see that they're nice and rounded. They don't have the hard edges that the Voronoi gives us by default. We can do a lot to edit the curves and kind of take it away from just what it gives you and add some more creativity, into the process. Right now, let's just disable this pipe component for a second and go back to just the Voronoi component so we can just see the curves. There's a lot of things you can do to affect and change curves so they're not just these hard edge poly lines. We can kind of soften them. We can smooth them out. So under the curve tab, under utilities, there are a lot of things we can do to affect curves. Mainly this section down here for today. So we can use this component called smooth polyline. And what this will do is it'll round off all the edges, make them more circular. So we can start by plugging the cells, the curves, into the polyline to smooth input. So we want to smooth these polylines. And we can see it's starting to do that. But it's kind of just making everything smaller and more circular, which is fine. It's nice. It is something. But maybe it's smoothing a lot, like too much at this point, and we could just want to smooth out the corners, maybe. And one thing we can do to do that is, if you know anything about curves in Rhino, the original curves, they have control points. So the points that make up kind of the kinks, kind of their edges, their points. And right now, each of them has only the number of control points that came with them. So this one would have 1, 2, 3, 4, 5, 6 points. And that's kind of rounding it off pretty heavily. What we could do, though, is we could rebuild the curve. So with rebuild curve, we could add our own number of control points. So we could take this number up a lot. And then it'll start smoothing it out a lot nicer, a lot less harsh like it is right now. So we can take those curves and plug it into the curves to rebuild. Right now, it's not going to do too much. But what we could do is we could take the number of control points and turn this up a little bit. Right now, each one has its own number of control points, but let's add a slider from, I don't know, 5 to 25, just something more than 10. And then as we take this up, it's going to add more control points, which visually isn't doing too much just yet. But if we were to use those rebuilt curves into the smooth polyline, now we can see we're getting just more kind of smooth stone, rounded off edges. It has a nice like inflated look, so the edges are still touching, but the points are rounded off. So it's a big difference from before, where it was kind of just making all of the points smaller. Now it's actually kind of rounding off the harsh points of them. We can control this strength. By default, the smoothing strength is at maximum, but we can control the number of times it does a smoothing operation with this T input. So this is optional, but just to show, there's a lot of things that we can play with all these different inputs. So right now, by default, the times is at 1, but if we take the times up more and more and more, we can see it's getting closer to like a perfect circle. If we went infinite, each one would become circles. But they're also getting smaller every time we do this. So up to you, like how much you want to smooth it. So that's just a nice step to clean up the curves. At this point, if we were to replace the curve input from the Voronoi with this new smooth polyline curves and turn this back on, we should see now that they're slightly more rounded out. Maybe it looks a bit nicer. So just some options of things you can do to change radius, change the look of the curves, change the density of things and all that. So yeah, slightly different look now. Again, the pipe component isn't perfect, so we do have these points kind of shooting off at random angles. But as we get later on in the semester, there's better components for things like this, the mesh pipe being one of them, that we'll explore in other classes. So that's the basics of the 2D Voronoi tutorial. Another fun thing, maybe you don't enjoy this translucent red color. There are some display options that come with Grasshopper that we can use to change this. So if you want to do like a custom preview, maybe pink's cool. If you don't like pink, there's another component called swatch that we could use to actually change colors on the fly with a HSV wheel. So could have it be any color you like. Just options. But so that's the 2D Voronoi tutorial. We can take a look at 3D Voronoi as we get closer to 7 p.m. today. Yeah, we still have some time. Any questions on the 2D tutorial? Anything that didn't make sense too much? Yeah.
The two components we put in the list item and the closest point.
Yeah.
I get why we did it, but I don't know how they would work.
Sure.
If you explain that out.
Yeah, totally.
Thank you.
Let's see.
Do you mind just repeating the question he asked?
Yeah, sorry, you guys can't hear too well. Maybe we should get mics for the entire room. But he has to explain what the closest point component is really doing. Yeah, it makes sense why we used it to clean things up, but I'll try to show how and what it's doing. So we'll turn on all of these points. Okay, so we have the, let's see, the original attractor points is what I'm going to call these points from the evaluate surface. So these are the ones that we can move around to attract the distance value, attract the radius. So we can move those with the MD sliders. Hopefully that's clear enough what this is doing. Once we get to the closest point itself, we have two inputs. So the points to start the search from, and in this case, we used the cloud of all the points to start from, and we want to look towards the two attractor points. And basically what we want to see is, if we say take this point right here, we want to see between the two attractor points which one is closest. So right now it's seeing that this one is finding that this attractor point is closest. If we looked at one over here, it's seeing that this one is the closest one. So the reason I set it up this way, so the cloud being to start and the points to search to being the attractor, yeah. The output here is going to output either the first point or the second attractor point. So we can see the list. It's either going to be 14 or 36 and just one or the other. So if we were to actually visualize it with the line here, we can see that these are the points we started with. These are the points we searched to. And then if we draw lines between those, we get that list of that diagram right there. So yeah, hopefully like building it, seeing it, and then moving it as well is going to like help see what's happening. It's really nice to see that transition line as we go between everything. Kind of like cut right there. So yeah. Doesn't that make sense?
Oh, yeah.
Good. I'm glad. Yeah. I hope that makes sense for everyone else too. Yeah, it's a bit of a heavy concept with like thinking about hundreds of points and hundreds of lines and finding closest between everything. But when we do attractor points, so again, you could use this in architecture, you could use it for fashion, you could use it for product design. if we're doing anything where we have attractor points, it's really nice to use this closest point to figure out, like, you know, what sets are different and what things are closest if we're using it for more things down the line, like the radius. So yeah, at this point, like, everything should be interactive. The pipe component might take a second to run every single time, but we have the control over the positioning, we have the control over the radius scale, the number of points inside everything, and then the domain itself for the radius of the curves. So a lot of different ways to control the final look of the piece here. So that's fun. So that's just 2D. Getting into 3D, it's pretty similar, but there's just another you know, direction to think about. We'll be using a lot of the same stuff though in this 3D tutorial. But instead of starting with a rectangle, we can start with a box this time. Very simple, just to start with a normal box. There's a lot of different boxes that we can start with that all show up here when we type in box. The easiest though, the nicest looking one is just going to be this center box. So this will just exist around the origin point in Rhino. So we can see we have that origin point there, we have that box. Again, same thing as the rectangle from before. We have the origin plane, so x, y, and then we have the x, y, and z numbers. We could put a unique slider into all three of these inputs, or we can just do a single slider for everything. So you can make the slider whatever scale you want. I went from 1 to 100, but if we plug that into x, y, and z all at the same time, then we get a nice scaling box that is all uniform. You could, though, do a different number for x, y, and z and have a different kind of rectangular prism if you're up for it. But it's not going to make any difference for this tutorial for a 3D Voronoi. Okay, so the most basic thing for 3D Voronoi is, well, first we'll need the actual 3D Voronoi component. So we can grab that blue 3D Voronoi icon and pull that into the scene. And then we'll have some fun with this with an MD slider and some other controls and all that. But basically all this needs is the point set and the boundary, just like the 2D also needed. So we have that boundary as the box. We won't really need it right now, though, but we do need some points. And we have those options that we saw before. We could use a populate geometry in this sense, but the only thing this will do is it'll put points on the outer walls of the box and nothing in the middle. So it's not perfect, but we could use the populate 3D in this sense. And if we add our points into the or add the box into the region input, we'll get points generated on the inside of this volume. And if we move around, we can see that we have points existing within the 6 walls of this cube. So that's cool. Hopefully that works. Should be pretty easy. Once we have the points, we can plug them into P for the Voronoi 3D. And instead of just 2D curve diagrams, we now have 3D cells. And it's doing that point perpendicular line in between points, but now it's doing it in all directions. So it's kind of hard to see exactly what's happening with them all together like this, but we've used this component in the previous one. You can use a list item to grab a single cell or a single piece of data out of any list. So we have the cells from the 3D Voronoi. We can plug that into a list item, and if we preview off everything before, just turn all that off, we can see that we're just looking at one of the cells right now. This isn't necessary for the workflow, but just to see exactly what's happening, we could use a slider to just scrub through all of the different cells of the 3D Voronoi. They're not going to be in any sort of order. It's kind of just random all over the place, but let's just find a nice one here. We can see from that original list of points, we have that one point that's existing right in the center of this cell. And if we look at all the points around it, we can see that it's found that mid-plane between the closest point next to it, and it's kind of done a facet of this volume at all of those middle intersections. So that's cool. But we don't need the list item. All we need is the Voronoi 3D here. I'll show you what we're going towards. Let's see. So what we can build today is this 3D Voronoi based on an attractor. So in this sense, we have this curve going through the scene. If we preview this off, we have this curve going through the scene. We have our box that we just made. And we can use this curve to select only the cells that are closest to it, again, based on a tolerance value, just like in the last one. But we can get this pattern to exist around that curve. And if we were to move this curve, the pattern would change and we would pull out different cells around that curve. So we'll build this and see what it's doing here. What does the rest of this do? We can also do the same thing as in the 2D diagram where we were doing different densities based on the circles. We can do the same thing here, and we can do a higher density just around a certain point. So in this case, it is right here. So we can have a higher density within this box, and then everywhere else will be a little bit lighter. So we can see quickly how to build that up as well. Okay, so we have the center box. What we can do is we can use
Can I ask a question?
Yeah, Joe, what's up?
What are the design implications of kind of doing it this way? Like what eventually like can you get out of it in terms of using Voronoi in a 3D pattern or in a box?
Yeah. So I mean, there's a lot of things you can do with the Voronoi. I do it for class because it's an easy, fun pattern to do like on the first day of Rhino. But if you want to make really cool stuff with it, you could look at, let's see, you could look at the stuff from like any of the lattice structures from maybe some printed shoes. Or there's also, let's see, if I can find it. Yeah, so like the support lattices inside football helmets or support lattices inside other kinds of padding. You could do a Voronoi diagram very simply to generate something like this. A lot of these examples, though, they might be doing something more complex with it too, but a Voronoi would be like the simplest option. And for some stuff like this, if you have or want more, I don't know, protection like around the ears or something, you could do a higher density point of cloud of points in that section and kind of have a higher density there and change it around with attractor points and things like that. So this is just a couple use cases for like some of the more cutting edge, I guess, 3D printing tactics that you could use. So fun stuff to show. But in terms of like, I don't know, very traditional architecture type things, maybe not too much, but up to you how creative. We did a project last semester with a student who's doing a facade based on a 2D Voronoi diagram. Did that kind of answer your question? I mean, there's a lot you can do with it, but there's also a lot of different diagrams that you could make that might, solve a question that you have or solve a site issue that you have a lot better. The Voronoi is a very overused pattern just because of how easy and simple it is and how interesting it looks. But there's a lot of other patterns that you could create more custom for different environments. But a lot of the kind of attractor points or different densities could still flow into other workflows that don't have a Voronoi per se, but some other kind of lattice structure.
Yeah, it seems like it could be used to kind of 3D print something with like strong qualities, but also kind of maximize the 3D printed material.
Yeah, you definitely could do that. In the lecture I gave on the first day of class, I think there was a picture of a cane, a 3D printed cane in there that utilizes a variable density. So it's strong where it needs to be, but lighter where it doesn't need to be. So it's easier for the user to carry around. So that's a nice use case. Yeah, materiality, cost, all that too. In like high-end 3D printed items, you could change a lot with that if you're not just talking about, you know, cutting wood or something. If you're actually designing every step of the process, there's a lot you could think about. So yeah, it's cool. Okay, any other questions? Yeah. It could. There's a lot of plugins that you could put in Grasshopper if you want to do. You could do sun analysis, like of a sun on buildings throughout the year. You could do stress analysis. If you have a GPU, you can do structural optimization as well. So you could give it just like a block and say, you know, there's a force here, and you need to attach a wheel here. What's the best way to like design a car frame? And it could like find that stress and make something nice. But yeah, I'd say like Rhino's a nice software to have. Grasshopper's a cool plugin, and there's so many things you can plug into Grasshopper to make it do like really whatever you want. You know, you could take your heart rate through here and like have a model change based on your pulse or something. I don't know. Yeah, there's a lot you can do with it. So, and we'll explore a lot of it this semester too. This was like just the first kind of easiest plug and play thing that comes with Grasshopper. So. Okay, so let's keep going with this. Let's see, the easiest way that we can, actually we won't do the MD slider because we already did that. Another way we could define an attractor point that might be a little bit more intuitive in 3D is to actually move a point around in Rhino. So if you grab this black hexagon point component again, and you'll notice we've used a black hexagon component twice. All of those are different parameter inputs. So this is kind of the most basic form of geometry number point that you could use. So let's see, with this, what we can do is right click on it and we can actually set a point in Rhino itself. So if we right click on the icon, hit set one point, you'll see up here, if you've used Rhino, you know that there is a command line up top that you can use to type in commands, but it'll also ask you questions up here when you do a command. So in this case, right now it's asking for a point location. I'm not sure by default what it shows for you. It might be curve, it might be point, or coordinate. But let's see, if you have a point in the scene already, you could reference the point. But the one I like to use is coordinate. So we can hit coordinate, and then we can just click anywhere in Rhino, and we'll get a point coming up. In there should be green. If you click on the point parameter itself, we'll get arrows that come up, and we can actually use this to move the point around in 3D. And this is controlled still all through Grasshopper, so there's nothing actually in Rhino just yet. There's no geometry in there, but it is nice. It gives us this control. So we can use the little handles to move the point somewhere within the box. Just anywhere inside will work nice. And we can use this in the same way we use the MD slider in the last workflow to make a point of higher density. In this case, we can't just use a circle again to make higher density. I mean, we could, but it wouldn't be 3D. In this case, though, we could use another center box to define a 3D volume that we could populate with more points. And by changing the number of points, we can make the density higher or lower in that area. So if we take the point and plug it into the base plane, it'll give us a box, albeit a tiny box in this sense, within our larger cube. So again, it's the same as last time. We can use a slider to change the size of that box. but we'll probably want it something a little bit smaller to just be inset within the box. It could be larger, but up to you. Anyone having issue with getting that point set? Yeah, so if you click on the point in Grasshopper, the little arrow should come up. But it all depends on how you set the point. You have to make sure when you're setting the point that it's in coordinate mode up at the top. And I can do it again. So if you set one point, as long as it says type coordinate up top, if you click it in, it'll give you a green point. And then if you click it again, it'll give you those arrows that we can use to drag it around. Hopefully that works. Yeah. Okay, so now that we have the center box, again, just like the last one, we can populate it using populate 3D. We'll get more points on the inside there. You can use a slider if you want to change this again, or you don't have to. 100 is it's a high number. And at this point, we could use the same thing as before. So we can cull those duplicates just in case there are any points that are too close together. So same thing as before, it just needs a tolerance value. And we can use both sets of points. So the points from the populate 3D we just made and the points from earlier, from the original cube. We can plug those both in holding shift or using the merge component again, just to make sure they're both in there. And we'll also want to make sure by hovering over the P input that we're not getting the data coming in on separate branches. If you see like list 0, 100 points, list 2, 100 points, then that's wrong and you'll have to flatten it to get them all to be together. But hopefully it just looks like this where we can see that we have a bunch of points just all together. With this, we can, again, move the tolerance slider if you want to cut down on the overall number of points. But that should be good enough. Now we have all the points together, and we can run that back into the Voronoi. And at this point, we'll get the Voronoi. It might not look too different because we still have that same bounding box, but on the inside here, we have a high density of cells right around the area of that point. Kind of hard to see, but we have some smaller ones around here and then larger ones as we get farther away. Let's see, as we move the box, if you move it outside of the boundary of that original cube, it'll make the box bigger as well, which might be something you like, but if that's not what you're going for and you just want it within that original box, again, we have the option of having a boundary for the 3D Voronoi, and we could use that original center box just to bound it back. So even if the point comes outside of the original box, the overall diagram is not going to get larger with that movement, so it'll keep it bounded. Okay, so now we have our final Voronoi diagram. The last thing to add is just that attractor curve at this time. So now we'll be using an attractor point for density and an attractor curve to actually pull out the cells that are around that curve. So hopefully from this tutorial you know how to set curves in Rhino. We'll actually draw a curve with any of the curve tools. So by grabbing a curve tool, let's just draw a curve, any shape, just inside the rectangle or the box. Once you're done drawing, you can just hit enter and we'll get a curve that is in there. It doesn't have to be fully inside. It's fine if it comes out.
So did you do that in Rhino?
I did do that in Rhino, yeah. Yeah, I did it in Rhino just because it's the easiest way to draw a curve. You could draw a curve from Grasshopper. We could set points. We could draw a Bezier curve. We could draw an interpolated curve between the points. And you would do that if you needed that control. So if you needed the control in Grasshopper to draw the line, then I would put in the effort to draw that curve. But just for this example, since it doesn't really matter what the curve looks like or where it sits, it's just really easy to draw it in Rhino. And we can rotate it to be, to sit however you want on the inside. Doesn't matter too much. Looks nice like that. So at this point, we can use the closest point component in a different way this time, and we can find what cells are closest to the line in order to delete the ones that are too far away. So last time we used it to control radius. This time we can use closest point to control if we keep the cell or not. So we'll just grab a closest point again. So as you're grabbing that, I'll just explain a little bit. The closest point, as we know, it needs points to find, what's close. But right now we have a curve and we have the cells, which that's not going to line up because it's not points. So we'll have to actually convert the curve to points that we can use to then sample to see how far away it is from the points that are on the curve. So in order to do that, we'll need to get the curve to be in Grasshopper itself. So you might have done this in the videos from last week, but if we ever want to take something from Rhino and put it into Grasshopper, we'll need to use a parameter to do that. So one of these black hexagons. We kind of did that with the point, although we weren't taking anything from Rhino. In this case, we're taking the curve from Rhino itself. So if you just type in curve into Grasshopper, we'll get a black hexagon that just says curve. And we can use this to hold the point, or to hold the curve in Grasshopper itself, even though it is actually in Rhino. So you can click on the curve in Rhino, and then with the component in Grasshopper, if we come down, same as with the point a second ago, but if we hit set one curve, it'll take the curve we have selected, and it'll bring that into Grasshopper. So now, if we click on that, we have the curve showing up as green, showing that it actually is instanced into Grasshopper as a curve. So that's working well. If the component is yellow or red, or if the curve is not lighting up green, then you didn't select it correctly, and you can just come back and right-click, set one curve, click on the curve, and now we have it set in Grasshopper. So hopefully that's working. Okay, at this point, just a couple more things to do for this to make it to work. We'll have to actually convert the curve into points, like I said. There's a couple different ways to do that. In the last tutorial, we were looking at utilities for the curve, so different ways to affect it. In this case, though, in division, there's multiple different ways to break up a curve into points or into smaller segments. The simplest one, though, is just the most basic divide curve. This will divide it into equal length segments based on the amount of point numbers that you set. By default, it'll set it to 10 segments, so 10 points. Let me just turn off the Voronoi so we can see this. But if we look at the curve now, with that divide curve turned on, we can see that it's divided it into 10 different points right there. Now, we can change this value if we wanted to, but for our case, 10 should be close enough. It's not the highest detail, but it should work for this. So same as before, the last time we used this, we'll want to use these points as the attractor points. So the attractor points will go into the lower input C. So these are the points we're looking for. So just like before, attractor points into C. The cloud of points, so in this case, the points that define the Voronoi, so the whole cloud, will go into P. And now we can visualize it again if you want to. You don't have to, but if we visualize it, we can see we now have kind of clusters of points that attach onto the curve as we go around. So now we have a lot more attractor points around this curve. Last time we only had 2. So same concept as before, just a different way to utilize it. In this point, as I said, we're going to use this curve to either keep some of the Voronoi cells or delete them. So if you want to delete anything, you'll use any of the components called col. There's a lot of them here, but in this sense, we'll be using col pattern. And col pattern, let's just grab that. It'll take a list. So we have a list. We have the list of the Voronoi cells. And the pattern is going to be true or false. So true, it'll delete it. False, it'll not delete it. So we'll just need to construct that pattern. And we'll construct that in a second. In order to do that, we can use the distance again. So if the cell is too far away, we can delete it. If it's close enough, we can keep it. But how do we define like what's close and what's far away? There's multiple different ways to do that. Some of the simplest would be smaller than, which I'm sure you're familiar with, or larger than, which you're probably also familiar with, just smaller or larger than a certain number. You could use those, or you could get a little bit more detailed, and we could use the includes component. So we looked at domains in the last tutorial. So a domain was a lower bound and an upper bound. And we can do that again here, and we can use a domain to define the distance and if we delete it or not. So we have those distance values again from closest point. We have all the distances. We can use those distances as the values to test with. So v values to test for inclusion. And we just need to define what inclusion is. So what's the lowest we will accept and what's the highest number we will accept. And we can do that with again, construct domain. This will allow us, again, to construct the domain that the values will sit inside of. In this case, we'll have to define what the A and B values are. I don't really know what a good number will be. So when you're in that situation, you can just go for really small and really big. So we could use a slider, say from 0.01 to 100. It's pretty small and pretty big. And then we can rein in these values to figure out what actually works well. But we'll just start really far out. So use those for A and B. A is going to be the lower bound, B will be the upper bound, so we can just move those sliders accordingly, A being really small, B being really big. And we can use that domain. I have now a domain that goes from 0.01 to 100. We can use that as the domain to test with in the includes component. And visually, I mean, it doesn't make too much sense what's happening right now, but we can visualize this by plugging in the includes output. So you can see now we've generated a list of true false values. The domain is quite large though, so we're probably including everything. So we get a lot of trues. But we can plug this into the pattern now that we have a list of true false values. So that'll accept that nicely. And then we'll want to either keep or delete the actual Voronoi cells themselves. So all of this. We're not going to see this happen though if we have this component previewed on. So it's best just to preview this off so we don't see any of the cells because we're going to be deleting some anyway. So we can take those cells, so the C output, the cells of the 3D Voronoi diagram, we can plug that into the list, so the list to col. Right now, since the values that I have are quite large, nothing has happened, but if we bring down this upper bounds, so keep bringing it down, you can see at some point it'll start deleting the cells that are too far away. And as we make this smaller and smaller, it'll try to hug that curve a lot nicer. It depends on how dense your overall point cloud was. If it was super low, like say 10 points, you're probably not going to see it hug it too much because the cells are massive. But the higher those numbers were further populate, we'll see it's kind of hugging it more. And we can see in that section where we had that point from previously, it's very dense around there. And we could move this as well to change that density, change where that dense section is. Yeah, and we can see now, hopefully it should be tracking just around that curve. If it's not, let me know. But if you're not seeing anything, you might just have to pull your sliders around a little bit until you find what values work for you, for however big your initial box was. Okay, so if that's working, there's a couple other fun things we can do just to like visualize this finally and close out this workflow. Two things that I think are interesting with Voronoi diagrams is right now, they're all touching each other. They're all right up on top of the next cell. One thing we could do is we could scale them all down, give them some breathing room in between. That might make the pattern look a little bit nice. And then the last thing we can do is assign colors to it. And we can do a gradient of colors based on the size or the distance from the curve. That would also be fun. So let's do both of those right now. The first one, scale. Scale is a fun component. It'll take a geometry, a center point, and then a scaling factor to do the scale. So we can grab that. There's a lot of different ones that we can use, but we don't need any of these more niche ones. We can just use the very generic scale with a single factor. And if we take the cells from the Cole pattern, plug them into geometry for the scale, let's turn off or preview off the Cole pattern so we can see just what the scale is doing. But we can see with no other inputs, it's taken everything and it's scaled it down around the center point of the origin. And it's scaled it down by a factor of 0.5, so it's now half as big. But that has really changed nothing. It'd be a lot cooler if all the cells scaled down around kind of their center point, so we can see that air gap forming in between them. So we've got a couple other inputs here. The center of scaling is going to be the most drastic in terms of what this looks like. And we'll want to get the center of all of the original cells. So how would we do that? How would we get that center point? The center point component is very self-explanatory. It's called area for some reason. If we grab an area component and plug in the cells, we'll get two things. We'll get the area, which we don't need, but more importantly, we'll get the center of the geometry. So you can see all those points popping up inside those cells. Looks pretty nice. You might wonder why, we had this original list of points to begin with. Why can't we just use that as the center points? And in our case, since we have cold, since we have deleted some of the Voronoi cells, we now, in my case, I only have 62 Voronoi cells, but originally I had 197 points. So if we tried to scale around 197 points, the list would not match up. We'd have way too many points and not enough cells to scale with. So it's nice now that we have 62 center points and we have 62 Voronoi cells. So those two numbers match, which is nice. So now if we do the scaling about that center point, so plug point into center point, now all the cells are scaling around their individual center points and not just the origin of the world. 0.5 might be a little bit too big, so you could do a slider. Any numbers you want, but just know that 1 will be no scaling. Anything lower than 1 will get smaller. Anything larger than 1 will get bigger. So we can use a slider here, and we can change the scale of these cells with that slider. Another thing important too about using an individual center point for each individual cell. The reason why it's working very nicely right now, every cell is scaling around its own point, and that's just because we've used the actual cells themselves to find their center points, so these lists match up. So cell in index 0 is going to match up with the center point that's also in index 0. If the lists were out of order, so for some reason, if the center points were, all jumbled up, then we would get very random scaling, which wouldn't be nice. But since we've set it up in this way, all the points align with all of their own geometry, so they scale pretty nicely. Last thing that we could do, which might be fun for visualization in projects, is actually adding some color to this. And I showed before how you can add color with the custom preview. But we can also add color. Instead of using a swatch, we can use a gradient in this case. And same thing with how we set up the center points to match with their individual piece of geometry. We can also set up the gradient to match the color value with each geometry that we have. So we have, in my case, 62 closed B-reps. We'll also want to make 62 different color values. And one way to do that, that is parametric, so we don't have to type in the number 62 every time we change the amount of numbers we have. We can actually get the length. Let's see. We can use list length to actually count how many items we have in a list. So list length will do that. We can plug in any list, in this case, the scaled cells. And this is going to tell us that, okay, we have 62 pieces of data in this list. So that's the first step for getting 62 different color values. The last thing will just be, if you remember from the very beginning of today's class when we reparameterized a list to be within 0 to 1, we can also reparameterize this list to be within the gradient value of 0 to 1 in this sense. And a way to do that with another math component is using a component called range. And what range will do, we've looked at reparameterization, we've looked at remapping. What range will do is it'll, by default, it has a domain of 0 to 1, and it'll take a number of steps and it'll break up the values of 0 to 1 to steps in between. So 0.1, 0.2, 0.3, however many you need to get to the final number. In our case, we can plug in the list length of 62 into the number of steps for the range. And that'll give us, in this case, 63 numbers coming out, which is not 62, which isn't perfect, but it's close. One thing we can do to explore another little detail of Grasshopper is, again, you can right-click on any input. And we've looked at reparameterization, we've looked at flattening. In this case, though, we can do something interesting. We can use the expression little icon here, and we can actually write a mathematical equation for the input to affect the input itself. In this case, we can do something very simple. We saw how we inputted the number of 62, but we got 63 numbers coming out, which is not the same. So what we could do with the expression is just take the input, subtract it by 1, and then the output should be 62, so both numbers will line up. In order to do that, it's very simple. We can use x just to represent the the number coming in, so the input value, and we can just say take x, subtract 1, and then if we commit those changes, so an expression of x minus 1, now we'll see that if you look at the number in the top of the range, it says we have 62 local variables. So now we actually have 62 numbers coming out, which tracks with the number that we had coming in. For some reason, the range component's just like this. But in this case, if we have numbers 0, 0.01, 0.03, all the way up to 1, now we've met all the requirements for the gradient value, for the gradient component. And now we can plug those color values into the material for the custom preview. And now we can get a colorful Voronoi cell. And there's a lot of different presets for the gradient slider. So we could change those presets and get different colorways. And we can also move around the points just like you could in Photoshop to change where the colors sit, to get different maps of colors onto our set of B-reps. And this color is pretty random, but you could also use the control points. You could use the scaling factor to actually say, you know, maybe the smallest one is a dark green and the biggest ones are very light green. You could do that with everything else we did today, but we do not have time to get into that. So we have random colors, but still another way to do colors in Grasshopper. So that's all I had for the workflows for today. People have asked before, there is tiny homeworks for the first couple classes just to make sure you're getting like an understanding of what's happening in class. So let me find those. So I have a couple of these things called challenge crates, and I've got a item in Discord where I'll post these in this channel. I'll just post the file for this. Basically, all this is just a way to try your own hand at assembling components and meeting some requirements. These will probably be very easy because we did all this today basically. But these are split up into 3 different sections in terms of what I think is easy, intermediate, and more difficult for challenges. But everything in here is what you'll get in the file as well. And just try out combining things and constructing, you know, what this description is. There's other things to help here with how you can build these. And on the right here are visualizations of the answers for these. So you can see the first one should look something like this. It's just using 2 different points to construct a line. So that'll construct a line. Next one using sliders to construct a line. So we can see it constructs a line. And then the last one, just trying your hand at different data structures in Grasshopper and how you can construct a ladder with points and sliders. So you can look here what they should look like and just try it out. There's no grades on these really. It's just to help you get an understanding. If you have questions, feel free to post those in Discord, or we can meet on Zoom to take a look at these things together if you're having issues. But I'll post this after class today, and I'll post the recording as well. Other than that, though, I'll see you next Tuesday. So enjoy the week.
Thanks, RJ. Have a good one.
Welcome.
Thanks,
See ya.
RJ.
Bye.
See ya.
Yep, thank you.